All right, welcome back to Geography 201, Chapter 14, Part 3, and now we're on to earthquakes. So, the areas that have earthquakes aren't quite always as obvious on the surface as volcanoes, but oftentimes can be more so dangerous. So, a good example here is Haiti. There are many small faults in this area. Haiti happens to be right on top of them. And there was an earthquake here in Port-au-Prince, which is the capital. And I believe this was in 2000, I want to say 2008. But when it happened, due to many circumstances, not just the earthquake itself, but the lack of building codes they can enforce in Haiti, that over 10,000 people died. Or I'm sorry, 100,000 people died. So earthquakes tend to happen if you map them. These dots are all earthquakes. They're basically a map of the edges of the plates. So earthquakes, for the most part, happen near the edges of plates, either where they pull apart or hit. Now, that's not to say they don't happen in the middle of plates. So here's one called a hotspot. We're going to talk about that. And the biggest earthquake in North America, the United States, ever recorded actually happened in New Madrid, Missouri, which is on the southern tip of Missouri in the year 1812. The reason we don't hear about it was that in 1812 there was almost nobody living there but Native Americans. So earthquakes happen at faults, right? And these are like the areas where plate boundaries meet. And there's three types. We talked about them a little bit. You have a normal fault where two pieces of the earth are pulling apart, right? Or like a divergent boundary. You have a reverse fault where they're being pushed together like that, and maybe sometimes one slips up like that. And then the last one is the slip strike fault. And that's kind of where they're going side by side on the surface. Like one's going this way, one's going that way. So here's an image. This is the normal fault right here. This block is pulling this way, and this block of earth is pulling that way. So they're pulling apart. Here they're being pushed together, and sometimes when they push together, maybe one might slide over the other or under. And here they're going side by side. Okay? So what does that look like on the surface? Sometimes you can't see it. One of the things you can see are what they call these indicators or scarps. When the rocks pull apart and break, they kind of fall over on their side, and they create these row ridges that are called gabens or gravens. So they look kind of like mountains, but a geologist trained eye can tell you that there's something here is causing this area to pull apart. This whole area of North America, even though it's not pulling apart like a plate, it's being stretched like taffy. Okay? One of the more obvious ones is a slip strike fault. And right here, here's the crack. This piece of earth is here, and this one moved that way. As you can see, here's the track for one side of the road, and then it moved up this way. And this is a lot like that sidewalk I showed you, that video where that teacher took his kids out to the sidewalk in Oakland every year. So how do they occur? When two faults, when they meet, or pull apart, or slide, right? They just don't move smoothly and easily. They kind of bump and move, and they maybe get stuck. And when they get stuck, stress happens. And if the stress gets too much, the rocks actually break. And that release of energy, right? They call that elastic rebound theory. And what happens is when the rocks finally break and move, the energy is released in the form of seismic waves. Okay? And that's what we call an earthquake. So here we have a piece of rock, and this side's going this way, and that side's going that way. So imagine a broomstick or a twig, right? Let me take my pencil. Here's like a pencil, right? And it wants to go like this, and you've maybe done this with a pencil before, and you can feel it, right? And here we go. So you're pushing it, and it bends and bends and bends, and eventually, if you give it enough force, it breaks, right? And that break, that snap, I just ruined a good pencil. But that snap, that releases energy, and it ripples through the earth in seismic waves. And that's what an earthquake is that release of energy, right? And so seismic waves travel through the earth, and we can detect those. Where the break actually happens along this boundary, that's called the focus. So the focus is the centerpiece of the earthquake. It's where it happens. Now, many people think that that's called the epicenter. but it's not. The epicenter is the area on the surface of the Earth that is directly above the focus. Because earthquakes can happen all along this boundary, so they can happen right at the surface, they can happen hundreds of miles underground. And if it happens over here, or here, right, even though the boundary on the surface is here, it's actually directly above under this. So the epicenter is often the area that's directly above it. It may not be the surface boundary of the plates, but it receives most of the strength of the earthquake. So that's the big thing. The focus is where the earthquake actually happens, where the epicenter is the area on the ground directly above it. Okay. Sometimes when these earthquakes happen, as I was bending that pencil, right, and maybe you've done this, as you bend it, right before it snaps, sometimes you can kind of feel the fibers kind of going inside, like ding, they're kind of getting close to breaking, and that's called a foreshock, a tiny little earthquake that predates it. And then oftentimes after everything moves and it rattles and it kind of settles down, those are called aftershocks. And they're basically smaller earthquakes that follow the main one. Oh, hold on. So, as we talked about, most earthquakes occur along the plate boundaries, called seismic belts. Okay? And those happen where the plates either collide or pull apart. They can also happen in the middle of plates and hotspots. So, seismic waves, there's different types. And the first one is where the waves travel. So, some waves travel right through the earth. An earthquake happens and a seismic wave travels right through the middle of the earth to the other side. That's called a body wave. We have P and S for those. And then there are seismic waves that once they hit the surface, almost like waves on water, follow the surface. And those are surface waves, obviously. And then the other way we look at them is how they move. Okay? So compressional movement, think about this. I think about a slinky or a spring. It kind of moves like this, like a spring would move. Right? So it compresses and then moves, compresses and moves. Whereas a shear wave goes like this, back and forth. So let me show you these images. Here is a P wave, and the ground's moving this way. So it kind of squeezes here, expands here, so it kind of goes joot, 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 joot. Whereas an S wave kind of goes like that. So on the surface, sometimes you'll see it like this, the ground will move like that, right? Compressional waves. Or you might have a shear wave where it's kind of going like this. Okay? Now, the device that measures this is called a seismograph. It's a very sensitive monitor, and it basically monitors ground shaking. So if you've ever been in a building and someone in the same floor has stomped on the floor and you can kind of feel it, your foot was a mini seismograph. That's kind of the same idea. You're sensing those vibrations, and that's what a seismograph does. And so what happens is it measures these on a piece of paper. And so when an earthquake happens, the P waves that go through the middle of the earth, those come first. They're the fastest. So if an earthquake happens, we get those between 2 to 3 seconds before or after. Then we get the S waves, and then the surface waves, the big ones, are the last to come at 4 seconds. So can a seismograph detect an earthquake before can we get early warning? By about 2 seconds, which is not really useful. Right? So that's what seismographs do. And what happens is this. Basically, you have this arm bolted to a table on the floor, and you have a pen hung by a wire. Trying to not knock my face. And when an earthquake happens, it makes the table shake underneath this pen, and how it measures the marker is right here. And so that's how we measure the waves. So, how strong are earthquakes? It all depends on many things. How much energy was in that movement? Was it a small piece of crust that moved? Was it a huge part? The Japanese earthquake in 2010, I believe, moved Japan 6 feet west. So the whole island moved by 6 feet. That's a lot of movement. Also, what types of rocks? Some rocks break easier. Some are much more brittle and just kind of crumble. How deep was it? How far away are you from it? So a lot of different factors intense it. So you can have a different type of earthquake on the same fault in different areas. Now, one of the ways we measure those is called the modified Mercalli scale. I'm not going to go into this too much because I'm not going to really quiz you on it, but this is kind of like how we monitor tornadoes. We don't actually measure it, we look at the results. So after an earthquake happens, they look at these levels. But the one that you're probably all familiar with is the moment magnitude scale, or often called the Richter scale. So, for instance, the Japanese earthquake that in 2010 was an 8.0 on the Richter scale. And this basically, we look at data from around the world, seismographs from all over the world. We combine them to look at the overall energy released, and it's an order of magnitude. And so what that means is it just doesn't go 2, 3, 4, 5. 3 or a 4 is 10 times stronger than a 3. And a 5 is 10 times stronger than a 4. So 10, 100, 1000, it goes on and on. And this shows you various earthquakes throughout history, how strong they were. So the one in Japan that I keep on talking about, the shut down the Tokushima reactor, was a 9.0, one of the strongest earthquakes ever recorded. It was actually stronger than the largest atomic bomb ever released. Mount St. Helens here, in comparison, the energy release was about as big as the San Francisco earthquake in 1906. But it just shows you right here that the amount of energy right here is 0.41, 12.7, 400, 12,000. So the difference between a 9.0 and a 9.5 is extremely large. One of the most odd things it can do is if the conditions are right, it can make the soil turn into quicksand. Literally quicksand, like I was joking about. What happens is if the particles of dirt are in the right size and shape, when they're shaken by the earthquake, it's almost like playing with mud when you're a kid. And the ground can kind of turn into this slurry, and buildings will actually sink into the ground. Okay? So, what do people do to take care of themselves? This is our safety quiz. Doubt that we're going to have to worry about it in Illinois. We do have earthquakes, just not that major. But basically, what people do is just eliminate the damage from other things falling on them. So one thing I was joking about, I said that we know about 1 or 2 seconds beforehand if there's an earthquake. In Japan, they have these little devices put on gas stoves that take that 1 second warning and shut off a gas stove. Because one of the biggest problems with earthquakes is when an earthquake hits, it causes gas lines to break and leak natural gas and starts fires. And the problem is sometimes there are also water pipes that have broken, so there's less water to put them out. In 1906, there was a huge earthquake in San Francisco, but the biggest cause of disaster were fires that started from gas leaks after the earthquake, and there wasn't enough water to put them out. So in Japan, whenever they build a house, they put these little tiny monitors on all gas lines, and if an earthquake is detected, they shut them off right then and there with that 1 second warning, and that's enough to stop gas leaks from spreading all over the country. But the big thing is that engineers design buildings to stand shaking. Some things can shake better and not fall down. Okay? In fact, in the US, in areas like California and Washington, where they have constant earthquakes, if you build a house, you have to design it to be stronger so it can have that. Okay? Or they take older structures and they make them stronger. They add reinforcement to it. But one of the issues is a lot of countries don't have these laws. Either A, they just don't have the ability to do it, so they don't enforce them, or they just don't have them. And that's one of the issues that happened in Haiti. Their buildings were not built to withstand earthquakes. A similar strength earthquake hit Mexico City within 5 years of the one in Haiti. And the one in Haiti that killed 100,000 people only killed less than 1,000 people in Mexico City. So, go back to my one question. Can we predict earthquakes? No. But what we can do right now is measure the probability of an earthquake. So this map is California, and what they're showing here is based on all the data. We know where faults are, we know what type of ground there is, and we look at this. And what is the probability within the next 30 years of an earthquake of certain types of magnitude? So in other words, the darker the red, the greater the risk there is of earthquakes happening. So what that does is it doesn't tell you that it's going to happen, but what are the odds? It's much stronger here than here. But the damage it can cause can be severe. This is actually a double-decker highway. The whole second level just fell right over here in Japan. Here in Chile, the bridge collapsed. So we're going to end this chapter kind of talking about what I talked about at the beginning, 1814, the year without a summer, right? So right here, Mount Tambora is in Indonesia, and this is it today, but it erupted in 1815. Okay? Now, another volcano, let's go back by the way, is Krakatoa. This volcano is very famous. It erupted in 1883, killed 36,000 people. The eruption was so loud it obliterated an island, and they could hear the explosion over 3,000 miles away. So by comparison, imagine if that volcano was in Los Angeles, they would have heard it in New York. But Mount Toba, it erupted in 1815. We'll talk about that to end this chapter, but it also erupted 73,000 years ago. That was the largest known eruption that we have evidence of, ever. So if you look at here, here's 1815, right? This is about 400 miles. Up to almost 1,000 square miles away from the volcano was covered in 1 foot of ash. By the volcano itself, up to 50 feet of ash fell. Now, most of that fell onto the surface, but much of it got thrown up into the atmosphere. And what it does, it acts like a sunscreen. It blocks sunlight. So we had a cold summer, 1816, year without a summer. And this just shows you that year, what was the average temperature? The darker the cold, as much as 3.5 degrees or 25 degrees cooler than normal through most of Europe. And so some of the things we talked about, it was so cold that there were very few farmers that were able to grow crops. Crops failed. People starved. There was famine. There were revolutions in the next year that some people attribute to that. In North America, it was so cold that year that Thomas Jefferson, the third president of the United States, he'd been out of office for 4 years. He was a farmer. His farm failed. He could not harvest any crops. He went bankrupt and had to sell his books. And those books were the foundation of the University of Virginia that year. So wide-reaching effects. One of the things scientists try to measure is if a volcano of that size would erupt again, what would be the effects on Earth's climate? I mean, we are going through an issue of climate warning, but these are things that we always can't predict. So if this was to happen now, who knows what would happen? So, all right. Well, that's all I've got for you in this chapter. I hope that this format helped you out a little bit. You'll be able to access this as well as the regular PowerPoint in D2L. As always, if you have any questions, comments, concerns, send me an email, talk to me during office hours, or send me an email then, or during our virtual classes. So thank you very much, and have a good night.